sigma equals to 0, and minus gamma is a minus 1/2 equals to 1. So those are our right gauges. And so the first thing, before we will launch into the Raman Hamiltonian of the particle string in this gauge, so let's see the consequences of this, right? So first of all, if I write down the whole sheet metric, gamma alpha beta, so I'm going to get gamma tau tau component here, which depends on tau and sigma. Then I get gamma of tau and sigma, which depends on tau and sigma. Then I get gamma tau and sigma, and then here I will get gamma sigma sigma. And one of our choices that we made is that gamma sigma sigma depends on tau. Okay. So what we also will need is the inverse metric, right? So remember in a particle metric, in a particle action, the inverse metric enters. So I have gamma alpha beta equals gamma tau tau, actually, before we go into there, so let me continue here. So I know the determinant of gamma alpha beta must be equal to -1, right? So that's one of our gauge fixing conditions. And so that tells us that sigma sigma gamma tau tau minus gamma tau sigma squared equals to -1. Solve for gamma tau tau, which is going to be equal to gamma sigma sigma -1, and then here I have gamma tau sigma squared -1. Okay, so there are two conditions. Well, actually, so I have an arbitrary function here, and this function gamma sigma sigma depends only on tau. Does not depend on sigma. So now, what we will need the inverse metric. So inverse metric will take this form. I'm just writing down it in general. But now, I can plot this in there and just compute the inverse of the metric, right? And you allow me not to do this on a blackboard. So if you're going to do that, you will find out that this is minus gamma sigma sigma. And then I have gamma tau sigma, and so here I have gamma sigma sigma -1 minus gamma tau sigma squared. Okay, so this is just a simple linear algebra, take the matrix and compute the inverse. Okay, very good. So now we take a particle action as particle minus 1/4 pi alpha pi d tau d sigma. Then so there is minus gamma square root, then there is gamma alpha beta, and then there is del alpha x mu, del beta x mu. So the first thing, we're going to simply write down this particle action using this metric and imposing all the other biconjugation orders. So first of all, this guy equals to 1, so it will drop out. And so this guy equals -1/4 pi alpha prime integral d tau d sigma. Okay, so let's just look carefully. So first of all, alpha, I'm just doing a very simple algebraic manipulation, and if I copy carefully from my paper, I should not be making a mistake. Right? So this, so here must be tau tau. I will start tau tau, but that's minus sigma sigma. So I have minus gamma sigma sigma del tau x mu. And we first choose light cone gauge on the wall sheet, and then we'll move to a space-time. So then I have del tau x mu. So we have this piece. Then there is a piece coming from alpha beta. One is tau, the other one is sigma. That gives me a factor of 2. So I have 2. And upper indices here is the same as lower indices. So I have gamma tau sigma. Then I have del tau x mu del sigma x mu. Okay. And finally, there is a piece with sigma sigma. So I have plus sigma sigma with upper indices, so I must use this piece. -1, 1 minus tau sigma squared, and then del sigma x mu del sigma x mu. All right, so all I have done so far is just write down the action in almost HPs. Almost HPs. So now finally we want to continue and we want to note that this index as x mu is actually x plus, x minus, and xi. Right? So we go to our line cone coordinates in space time. And so what this immediately implies, that del tau of x plus is going to be equal to 1, and del sigma of x plus is going to be equal to 0. Right? So one of our choices is that x plus is exactly the line cone time. Good. So now we look at our Polyakov action, and we're going to collect various pieces. So let's collect ij pieces first. Okay. So I have minus gamma sigma sigma del tau xi del tau of xi. Then there is this other term plus 2 gamma tau sigma del tau xi del sigma xi. And then there is a third term, so plus gamma sigma sigma minus 1 minus gamma tau sigma squared del sigma xi del sigma xi. Okay, so I collected ij pieces. By ij, I mean those transverse coordinates to our right hand coordinates. Now, next, the only term that will be left is x minus. So now we're going to collect x minus term. The reason there will be no x plus term because x will always come with a derivative, and derivative of x plus will either be 1 or 0. So let's look at x minus. So in the first piece, I have x plus, so there will be a factor of 2. So I can let me just say what I mean more precisely. So I have x plus here, del tau x plus, which is the same as plus gamma tau, and then I have del tau x plus del tau of x minus. And actually there is additional piece which is minus and minus, right? So there is additional term del tau plus x minus del tau x minus. So this guy gives me plus gamma sigma sigma del tau x minus del tau x plus. And so now we're going to use simply the condition that this derivative is actually 1 in our likelihood gauge. So those two pieces together will give me 2 sigma gamma sigma sigma del tau of x minus. Okay. And so the only other place where x plus or minus can come from is from this term. Cannot come from this term because sigma acts always here on x plus, and del sigma on x plus equals to 0. So that actually tells us that there will be only one contribution coming from here. That's when this index mu is plus, so this guy is minus. And so the other piece is going to be, the other term is plus 2 gamma tau sigma. Then I have del tau of x plus, and then I have del sigma of x plus. So this guy is 1, and now I want to raise this index to go back to x minus. X plus is not going to be a dynamical variable, as in the case of point particle, it's only x minus and x sub I. And so I have minus 2 gamma tau sigma, and then I have del sigma of x minus. Okay, so very good. So we collected all the pieces. Okay. So now I want to introduce the center of mass position of the string. So what I'm going to do, I'm going to let's introduce, so the average position of x minus coordinate, I have x minus, so in general it's a function of tau and sigma, so I'm just going to define it as x minus of tau plus y minus tau and sigma. Okay? So the way how I did this decomposition, this is an average of capital X minus. So by definition, this is an integral from 0 to L d sigma of x minus tau and sigma, and I have one of the L here. So what this immediately implies, that an integral from 0 to L d sigma of y minus equals to 0. Okay, so this is just a convenient decomposition, as you will see in a second. Okay, so very good. So I want to use this document. Yeah, okay, so let's look at two terms in which x minus enters, right? So so there is a contribution. There is a term here, okay, and there are two terms where x minus enters. So let me write them down. There is 2 sigma sigma del tau x minus, and then there is minus 2 gamma tau sigma del sigma of x minus. So now what I want to do, I want to ask how those terms will look like under my decomposition when I separate the center of string position for the x minus coordinate. All right, so let's look at this one first. So this term gives me del tau of little x minus plus 2 gamma sigma sigma of, so this is my first term. I'm going to call it A. This is the second term. I'm going to call it B. So for A plus del tau of y minus. So I'm going to show you now that this term doesn't matter. Okay. So why this term doesn't matter? Well, so remember that what we have to do, we have to integrate. We have to integrate with respect to tau and sigma of whatever the pieces I'm writing down. It's that integral. So I have this term here, del tau of y minus. Okay? So now you can see the benefits of the light cone gauge that we did. So remember that gamma sigma sigma depended only on tau, but it did not depend on sigma. So what I can write down, I can leave the integral with respect to tau outside, and then I can take out 2 gamma sigma sigma outside of the sigma integral, doesn't depend on sigma. So I will be left with integral with respect to d sigma del tau of 1 minus. Okay? And now I'm going to make one more step, right? So in this integral, so this is an integral of d tau to gamma sigma sigma, right? So I'm integrating with respect to sigma variable, but the derivative is with respect to tau. So what I can do, I can pull out the tau derivative outside of the integral, and so I will be left with sigma of y minus. Okay? And so now you can see beautifully, this guy actually vanishes. Because the way how we did our decomposition is the integral from 0 to L of y minus equals to 0. So this integral equals to 0. So I have del tau acting on 0 times whatever something else times the integral. So this guy equals to 0. Okay? So what we showed is that indeed, in this term A, this guy does not contribute. Okay? So which is very good. You will see why. You can see I hate this. I hate, well, this is what it's sometimes difficult that when you learn string theory and somebody tells you do this, and then, yeah, if you do that, you will get something nice and simple. Otherwise, things will be very complicated. It's, not at all clear why those steps must be done, but you will see at the end of the day, everything will be so simple. There's this stuff in between. Okay, so let's look at this B term now. So if I look at the B term, so I have minus 2 gamma tau and sigma del sigma of x minus, right? So now I'm just going to write it down as little x plus y minus, right? Of tau and sigma. And so you can see that there is simplification in this B term as well. So in fact, what is going to happen is that this guy does not depend on sigma. And so when I take a derivative of that, it will vanish. So the B term gets simplified, and it becomes minus 2 tau sigma y minus derivative. Derivative del sigma of y minus. Okay, so now I can tell you what is the whole reason we've been doing all this light cone gauge. So that's the place to see it there, actually the reason. So notice that this y minus coordinate, which is a non-trivial part of x minus dependent on a Walsh sigma coordinate, will not have a tau derivative as it enters in the action, right? So x minus, so y minus enters only through those 2 terms, and so we used our light cone in such a way that this term does not contribute. There is only x minus, right? Little x minus. There is no contribution from a complicated y that depends on the space-time coordinate. So this term would imply that 1 minus is our dynamical variable because it contains, there will be a conjugate momentum due to it. So that term vanished, And so the only contribution where y minus, how y minus enters in the action is with a derivative with respect to sigma. So what this tells us that y minus is not a dynamical variable, but rather it is a constraint. So it's a sophisticated Lagrange multiplier. Okay, so it's a sophisticated Lagrange multiplier. So it doesn't lead to any equations of motion, it just imposes constraints. What we will do, we will try to figure out now what are those constraints and what will be the upshot, so that it will be a constraint and it will lead us. I don't want you to get lost right now. So imposing the constraint due to variation with respect to y minus will lead us to condition that the off-diagonal piece of the bullshit metric is 0. Remember, we didn't have enough freedom to put off-diagonal pieces to 0. And that was a complication. We have lots of mixed terms, right? So you can see there is a mixed term here. This guy looks ugly. It has 1 minus x squared or something. And all I'm saying right now is that once we identify that y minus will be a constraint, I will show you now that that constraint will lead to an exact solution for the off-diagonal component of the metric. And in fact, in this Lightcone gauge, the whole purpose of it, if you wish, was to make sure that we can choose a diagonal metric on the worksheet. Okay, so now we have to see that. Okay. So how are we going to see that? Okay. So first of all, let's do variation. So let's do variation of the Polyakov action with respect to y minus. So just want to vary as Polyakov with respect to y minus, and I want to assign it to be equal to 0. Right? So the piece that we have to vary with respect to y minus, well, I'm not going to write down this. I like to write down my variations in the integral form. So this will be a variation of an integral d tau d sigma, right? And so the only piece where y minus enters is this term up here. So it's going to be a variation of minus 2 gamma tau sigma del sigma delta y minus, right? So that's the only place in the action where y minus will end.
Can I ask a question? As the Between metric is always conformally flat, I mean, the off-diagonal conformity is 0. If we can always
right. So you're right. I can use diffeomorphism invariant in such a way that the metric I can remove off-diagonal. That's absolutely correct. However, I guess a posteriori, what you will find out that the action is still complicated. Okay. My claim is that by choosing this Lightcone gauge the way how we did, so that we are at this stage we're still left with off-diagonal components. We will end up with a simple quadratic action, all dynamical fields, that one outcome, and well, the metric will end up being diagonal. So I haven't explored what would have happened if I would just do diffeomorphism invariant fixing, as you said. But that would not definitely be enough. In order for me to get to a physical spectrum, I would still need to fix wild invariants. And again, so we don't have to lose the track So there are various ways how we can quantize the string in various gauges, okay? And so we're doing quantization in the light cone gauge because the claim is we can get to the physical spectrum in the fastest possible way, which I think is true. So then we will do quantization in a covariant gauge. So, and it doesn't matter as long as you fix all the gauge degrees of freedom properly and you deal only with physical degrees of freedom. It doesn't matter what gauge you choose. The spectrum should be invariant with respect to gauge fixing. So let's continue, okay? But you agree with me that at this stage it's in no way obvious it's all diagonal component must be matched. Okay? So that's our purpose. So once I do this variation, so if I do this variation and so that leads, so the variation is there. So I have to integrate by parts. Okay? So I integrate by parts, and I will find del sigma minus 2 plus 2 del sigma gamma del sigma delta of y minus. Okay, and then there is additional piece. Okay, so then there is additional piece which will be minus 2 del sigma gamma. Sorry, derivative times delta y minus. So there is still an integral from d tau, and so here I have sigma equals 0, sigma equals 0. Okay, so I didn't change, right? So now I want to do the following thing. I want to look back at our boundary conditions. So, and see how the boundary, so what we did, we took a particle action and we rewrote it in the light cone gauge, but we have to do the same with the boundary condition. And in particular, we will look at the open string with the Neumann boundary condition, right? So that's the only kind of open string that we discussed with you is consistent with space-time covariant layers. So Neumann boundary condition in light cone gauge. So remember those conditions to this form. Del sigma of x mu was equal to 0. That's a Neumann boundary condition. And so I can write this down as gamma sigma sigma del sigma of x mu plus gamma sigma tau del tau of x mu. So I just wrote it explicitly. Now I can use the inverse metric written on the blackboard out there. So this guy becomes so gamma tau sigma del tau x mu, and then I have plus gamma plus gamma tau tau, right? So with the upper indices, so I have here gamma sigma sigma, which is gamma sigma sigma minus 1 sigma tau squared, and then I have del sigma of x mu to be equal to 0. So I haven't done anything. I just took Neumann boundary conditions and rewrote it in the light cone gauge. And so index mu should be over all dynamical fields. And so in particular of interest for us here is other two cases. So we're going to choose mu equals plus. So if we choose mu equals plus, and of course this must be at the boundary. So this is, I should write down, this is correct for sigma equals 0 and L. So we have a vanishing of these derivatives when sigma equals 0 or L. So if I choose mu equals plus, then I have tau sigma as a function, for example, of tau at 0. And then I have del tau of x plus minus 1 of tau, 1 minus gamma tau sigma squared of tau 0, and then del sigma x plus. That must be equal to 0 because of Neumann boundary condition. But the way how now you can see finally the benefits of choosing the Lycombe time. You know that this guy equals to 0, so all this complicated bracket drops out. But this derivative equals to 1 because our Walsh time is the same as the Lycombe time. And so the Neumann boundary condition implies that the off-diagonal component of the metric evaluated at the end of the open string Walsh actually vanishes. So this is true on both ends, right? So I didn't have the left end, but obviously you can do it for both ends. Okay? So that's a boundary condition when we put mu equals plus. And so that now, once I use this, so I can forget about this term altogether. And so for the, let me just finish with the boundary condition. When x equals to I, so this guy is 0, I will have gamma sigma sigma minus 1 of del sigma xi must be equal to 0 at the endpoints, right, when sigma equals 0 or L. Now, we don't want the degenerate metric. We should be able to take the inverse of the metric. So we have a Neumann boundary condition on the transverse coordinate of the string. Del sigma of xi must be equal to 0 at the boundary. Okay, so those are all relevant boundary conditions for us. So once we understood these boundary conditions, let's go back. And look at our Lagrange constraint. So let's look at our Lagrange constraint. So first of all, this boundary piece involves gamma tau sigma, but we just showed that if we impose the Neumann boundary condition, gamma tau sigma vanishes. So this term goes away. And so in order to satisfy the Lagrange constraint on y minus, or the equation of motion for the y minus, so EOM for y minus implies that an integral of d tau d sigma of del sigma gamma tau sigma of delta y minus must vanish for arbitrary function. Okay? So you agree? Okay. So naively you would have said, well, this is an arbitrary function, and so that from here this immediately implies that del sigma equals to 0. Okay? And that's incorrect. So this is wrong. This is wrong. And the reason why this is wrong is because the variation of y minus is not an arbitrary variation, it's constrained. Remember that our field y minus was constrained in such a way that when we integrate it over the whole length of the string, it must vanish. What this implies, it implies that the variation of that field integrated over the whole space coordinate on the string must vanish as well. And so actually, vanishing of this integral simply tells us that del sigma gamma tau sigma must be a constant, or in principle it can be a constant that depends on tau. See, if this guy is a constant, then I can integrate with respect to the sigma, and it will give me a 0. Right? So the constraint is not that the derivative vanishes, but rather the derivative of the off-diagonal component of the metric is independent of sigma, which is to say that del2 of sigma, gamma tau sigma equals to 0. So given this constraint, the correct equation on the off-diagonal component is this second derivative vanishes. So we have this equation. So this is a second order differential equation. And then we have a boundary condition. Right? So we have vanishing of the function at both ends. We have identical zero boundary condition, two boundary conditions, which is exactly the same order as differential equation. So the solution to this differential equation now everywhere must be equal to 0. If I have a second order equation and my function vanishes at the end, the only solution of that equation is that the function is identical to 0. I proved to you what I promised, that resolving the Lagrange multiplier constraint on y minus leads to the conditions that tau sigma, gamma tau sigma vanishes identically. Okay. So once we did that, then you can see lots of terms vanish in this Polyakov. And I have lost track of all the good black books, lost all the pieces. So you have to bear with me that. So now what we have that I'm going to put gamma tau sigma everywhere, everywhere in the Polyakov action. And once I do that, the action will take a very simple form. So first of all, I will find out that my action depends on the following fields. So I have x minus as a function of tau. I have gamma sigma sigma as a function of tau. Right? We haven't done with gamma sigma sigma anything. And then there are transverse coordinates. Again, I have done nothing there. Notice that there is no y minus, and the reason for that is we already solved for the equation of motion of y minus, and we flagged so this is from delta s Polyakov over delta y minus equals 0. So that we flag to that equation, of course, plus Norman bound. Okay, so if we do that, then the Lagrangian of the Polyakov action will take the following form: minus L over 2 pi alpha pi minus 1 4 pi alpha prime integral from 0 to L d sigma del tau xi del tau xi and minus gamma sigma minus 1 del sigma xi del sigma xi. Okay? So what I did, I wrote you the Lagrangian as a Polyakov action as Polyakov is simply the integral of the tau of this Lagrangian of the Lagrangian. Right, so the reason, so what I did here, you pretty much can believe me that there will be some integral. What you might worry is, where did I get this term? Well, notice that this term contains only the quantities that depends on tau. X there is a little x, so it doesn't depend on sigma. So what I did, I computed the integral with respect to sigma, and that integral simply gives the total x as a string out. So that's our starting point. All right, guys? So any questions up to now? So you can see already that things look very nice and very simple. So x is transverse coordinates and quadratically. Okay, so let's continue and find the Hamiltonian of the system. And I think that's where we will end. We'll discuss Hamiltonian equation of motion and canonical quantization next time. So good. So I identified the chemical variables, and so we can now construct conjugate momenta, right? So P minus is the same as minus P plus. So that's light cone momenta. So that's del L over del tau of x minus, right? I have to compute a variable conjugate to x minus, a conjugate momentum to x minus. So now, if you look at the Lagrangian that's given there, so that's simply minus L over 3 pi alpha prime gamma sigma sigma. Okay, and so what you see that P plus equals to L over 2 pi alpha prime gamma sigma sigma. So this is actually very similar to what we had in the point particle case. So what we had is that P plus was equal to minus eta minus 1, so it was related to the metric component on the string worldsheet. And so naively, we might have thought that gamma is a coordinate, but it's not. It's actually related to a momentum, much like in the point particle case. Okay, so very good. So now we can construct momenta conjugate to xi of tau sigma. And in order to do that, so that's going to be what I can call capital pi sub I, super I equals pi sub I. So raising and lowering transverse indices doesn't cost us anything. And so we have to take a derivative of a Lagrangian with respect to del tau of xi. And so if you look, well, actually here to be more precise, I need to write down as a variation of derivative. And so you can see that where does it come from? It comes from this piece, and there will be a factor of 2. The factor of 2 will be because I have del tau xi squared. So there is 2 over 4 pi alpha prime. And then I have gamma sigma sigma del tau of xi. And now what I notice is that I want to rewrite this answer including P plus. So that's going to be equal to so if I cancel 2 here, so I have 1 over 2 pi alpha, right? And that's the same combination as it's in here. So I have P plus divided by L times del tau of xi. Okay, so in other words, I can invert this relation. Del tau of xi is going to be equal L divided by P plus of pi sigma. Okay, so we are on our way to construct the Hamiltonian of the system. And so once we compute a derivative of coordinates, we want to express them in terms of conjugate momenta, and that's exactly what I achieved there. Okay, so we're all done, and the last formula we're going to derive today is actually a Hamiltonian. So the Hamiltonian of a Polyakov string in light cone H. is going to be equal to, so H equals P minus del tau of x minus, right? So here I have the center of mass coordinate, and then I would need to, so these p sub i's, they are not the momenta that's related to your question, but they are the momenta densities, right? In order to have the momenta, I have to integrate with respect to sigma. And so what this tells me is this tells me that in order to write this down, there is no sigma dependent here, but there will be a sigma integral here from 0 to L. So here I will have P sub I del tau of x sub I. So those are generalization of the point particle case, and minus the Lagrangian, that's minus the Lagrangian. All right, so this equals to. So where is my Lagrangian? Did I lose it? I erased it. Okay, so let me keep writing it. So it's P minus del tau of x minus, and it nothing with the first term. In the second term, I want to express the derivatives with respect to coordinate in terms of momenta. So I have P sub I times del tau of x sub I is P sub I times L divided by P plus. Okay, so that's the first two pieces. And then there is a Lagrangian. So where do I have Lagrangian? Did I? Okay, so that's going to be a challenge. I'm not that tall. So anyway,
you can just write down the items of.
We haven't looked at both things. I will think less of myself if I wouldn't do that. Thank you. Yes. So let's just follow. It's so simple that we can follow. So here there is this del tau of x minus. There is a minus sign. So now this term here is related to p plus. That's exactly p plus, including the minus sign. Okay, so this is just sorry, not p plus. That's exactly if I put the minus sign, so that's a p minus with minus there. So I have minus p minus del tau of x minus, right? So that's we get rid of this piece, and then there is this integral there. So it's minus, so this integral 1 over 4 pi alpha prime. And then I have an integral from 0 to L d sigma. Gamma sigma sigma I have to write down in terms of p plus. So it's going to be equal to 2 pi alpha prime p plus divided by L. Okay, so this is what was gamma sigma sigma, and then I have del tau of xi, and those guys are pi L squared over p plus squared. So that's the term that will come with minus sign. And then finally there is this term, which will come with a plus sign, plus 1 over 4 pi alpha prime. Integral from 0 to L d sigma. So I have gamma minus 1 of tau. So that's going to be equal to L over 2 pi alpha prime. Sorry? P plus will be in the denominator here, and then I'm doing nothing. Those are the. Okay, good. So I'm happy now. So that's our Hamiltonian. So now you can see that del tau x minus cancels as it does in the point particle case. And so here you can see that this term is exactly the same as the first term up here, right? So 2 pi alpha prime, and I have 4 pi alpha prime, so there is a factor of 1/2. Now, P plus, I cancel 1 power of P plus. I can cancel 1 power of L, and so it's exactly the same piece, and it comes with minus 1/2, right? Minus 1/2. So altogether, the Hamiltonian of the string will look like so we have H going to be equal to okay, so it's going to be equal to 1/2 integral from 0 to L d sigma L over P plus, and then I have PI and PI, and then there is plus there is another term which is L over 4 pi alpha prime squared, and then I have an integral from 0 to L d sigma 2L 2 over P plus del sigma x xi of xi. Okay, so very good. So so at this stage, this is what I would have to do, but let me do one more step, and I justify that step tomorrow, I mean next time, is that P plus is actually a conserved quantity. So from Hamilton-Jacobi equations of motion, from Hamilton-Jacobi EOMs, right? So we have a Hamiltonian, we can derive equation of motion. So what we will find out is that del tau of P plus equals to 0. So P plus is actually a conserved quantity. P plus is a constant. And so what I can do, I can pull out P plus of that Hamilton integral. And so once I do that, my Hamiltonian will take this form, L over 4 pi alpha prime P plus, and I have an integral from 0 to L d sigma. Okay? And so I have 2 pi alpha prime pi I, okay? And then there is a piece there, so that's plus 1 over 2 pi alpha prime, right? So I would have 4 pi alpha prime, but there is a factor of 2, so it will be 1 over 2 pi alpha prime del sigma xi del sigma of xi. Okay, so as I promised, when that at the end of the day, the Hamiltonian of the Polyakov string in a electron gauge will take a very simple form, and indeed we have just a square of momenta plus the square of a square of coordinates plus a square of conjugate momentum. All right, guys, so next time we'll start from here, and we'll derive equations of motion, and after that we do canonical quantization. Right.